High operating temperature is a widely known threat for the reliability of semiconductor components. The ongoing trend of vehicle electrification has brought the latest semiconductor technology into our cars, making them safer, smarter, and more efficient. In sync with this, the demand for high-quality components in the electric vehicle industry has increased. OEMs are looking at quality assurance practices almost matching military levels. They have only one goal in mind: keeping us passengers safe. Our group has been the supplier of the most advanced thermal test and simulation technologies, supporting OEMs, Tier 1 manufacturers, and component suppliers to optimize and better understand their thermal designs. I would like to introduce our latest characterization technology today, taking us from the thermal labs to the production floor. Our new thermal quality assurance system can test the integrity and quality of semiconductor components using short power pulses. The method combines thermal transient testing with industrial automation. The test system connects to a test handler, which is a robotic arm in this particular case. The test captures the thermal quality of the sample and compares it to a pre-selected reference set. The automated test and evaluation can be used in many situations when working with packaged semiconductors. Examining finished packages is one obvious application, together with inspection of incoming parts, filtering counterfeit components, and having an effective way to test a larger number of samples in a laboratory. We have created our workflow with all of these in mind and have an underlying architecture that can cater for even more when needed. First, the device type has to be defined. You can select diodes, silicon and silicon carbide MOSFETs, and IGBTs. Diode tests would cover most high power density IC applications as well. After setting electrical limits and the test parameters of the component, the system prompts the user to create a short trial test, which would later serve as a reference. You can select multiple bands around the signal, defining the binning limits during the test. The farther the actual signal is from the reference, the worse the quality is. Once the test parameters are set, an operator can easily load the test and binning definition and start the measurement. The components are loaded into a feeder or are supplied continuously in the production process. You can see the robot picking up a TO247 package in this example and placing it to the test environment. The end effector then presses the sample from the top, establishing both electrical and thermal connections. For die attach characterization, the thermal environment is less important. However, you can set longer pulses to capture the RTHJC of every single component. Once the measurement is done, the built-in computer evaluates the data and makes the binning decision based on the initially set parameters. The handler moves the component to its corresponding bin and returns to its original position to pick up the next sample. It is that simple. The robotic arm you see here can be replaced by any other model, depending on the size, weight, and speed requirements of the component to be tested. A discrete component, such as an LED, can be measured as quickly as 0.1 seconds, whereas to test the thermal grease in a larger power electronics assembly, pulse lengths up to a few seconds may be necessary. The concept is the same though, and the quick, non-destructive thermal tests are superior to any visual characterization methods. We only require electrical connections to the sample to provide real thermal information for every single device.